All right, so this is section, it's actually section 7-4. We're getting these notes off of a different version, so you're going to see different numbers and different page numbers for different things. But it's actually 7-4 in your book, which is Trigonometric Substitution. So I have these notes for you, so make sure that you print out this page of notes beforehand, unless you want to write it all down, which is fine with me, but if you don't want to take the time to write it down, then you want to print these out. So go ahead and do that first, and then we'll go ahead and get started. So the first section we're going to look at is called Trigonometric Substitution. So we will scroll down to that piece now. All right, so in the last couple sections, we talked a little bit about trigonometry and how it's involved with these radicals. So for this first section, it says, now that you can evaluate integrals involving powers of trigonometric functions, which we've been working on over the past couple sections, you can use trigonometric substitution to evaluate integrals involving the following radicals: the square root of a squared minus u squared, the square root of a squared plus u squared, and the square root of u squared minus a squared. So our objective, or our goal for these integrands, is the objective with the trigonometric substitution is to eliminate the radical in the integrand. So the goal is to eliminate the radical in the integrand. In doing so, because it's difficult for us to take the integral with these radicals, so in doing so we're going to be able to narrow it down to trigonometric functions only, and we'll be able to take those radicals fairly easily, or at least hopefully fairly easily. And we do this with the Pythagorean identities. And you know the Pythagorean identities, sine squared plus cosine squared equals 1, secant squared plus tangent squared equals 1, or secant squared minus tangent squared equals 1, I should say, I'm sorry, so on and so forth. So we're going to use these in order to help us as well. It'll be a little bit more clear when we come to an example, but let's keep going with this notes section. So trigonometric substitution when a is greater than 0. So we're not talking about a's being negative, we're only talking about the a values being positive, which because they're all squared, it's going to get rid of a negative anyway, so that's why we just talk about when a is greater than 0. What we're going to say is for the integrals involving this form, where you have a squared minus u squared, what we're going to do is we're going to let u equal a times sine of theta. And when that happens, then we're going to have a squared minus u squared equaling, the square root of that equaling a times cosine of theta. And this is going to be limited to the interval from negative pi over 2 to pi over 2. Now, it might kind of seem like we pulled those things out of thin air, the a sine of theta and the a cosine of theta. So I'm going to show you really quickly where they got those from so that it makes a little bit more sense to you. So when you have that written down, I'll flip it over to the next image. And this image that I'm pulling out of is actually in your book. It's on page 499 in your book, which is in section 7.4. So if you want to go ahead and look in your book for this picture, you'll see it on page 499. So it looks like this. Let me make it a little bigger so you can see it. So what we just copied down comes from right here. This number 1 is what we just copied down. So you can see that they're using the properties of triangles in order to get these values. So here's how I would go about trying to recall how they came up with these values, or how they came up with these substitutions. So it says for integrals involving this here. So, excuse me, when I see that, I'm thinking, okay, it has a minus, and if I'm thinking about the Pythagorean theorem over here, and if it has a minus underneath the square root, I know that my first value has to be the hypotenuse, and the second value has to be one of the legs. So that's how I know that a has to be the hypotenuse, because it was the first value right here, which was a squared, and I know that u has to be one of the legs, because when I look back at the Pythagorean theorem, excuse me, I have u squared plus, and then if I have this value here, the square root of a squared minus u squared equals a squared. And when I simplify all that out, I get a squared u squared plus a squared minus u squared equals a squared. And then the u squareds cancel and you get that a squared equals a squared. So the way that they've set up this triangle does work in the Pythagorean theorem, and that's why we're going to be using it. So like I said at the beginning again, the reason that we know to use this specific setup is because when I see that a squared minus u squared, I always know that my a is right there on the hypotenuse and my u is over here as one of the legs. Now, oops, I didn't want to do that. Now here's where I get these other parts from. For this part here, the u equals a sine of theta. If you think about the trigonometric rules in terms of theta, here's u, way over here. And if I'm thinking about it in terms of theta and the relationship between u and a, I know that sine of theta equals u divided by a. So if I try to solve that for u all by itself, I get that u equals a sine of theta. And that's where this came from right here. Alright, so that's all that I'm pulling from. I didn't come up with any fancy thing out of the blue. It's just from the simple trigonometry of the triangle that you're going to figure that out. Alright, so that's where that came from. And then vice versa, if we're looking at the second piece down here. So now if I'm looking right here, I have a squared minus u squared. The square root of that equals a cosine of theta. Well, again, that makes sense because we're looking at the relationship between these two sides, or the ratio of these two sides. So I'm looking at cosine of theta equals the square root of a squared minus u squared over a. And if I multiply the a to the other side, again, I get the square root of a squared minus u squared equals a cosine of theta, which is what I have right here. So that's where I'm getting those values from. If you ever forget what those values should be, you can just look back at the triangle and figure it out, and it should give you the same answer. So I'm not going to actually go through the next two, we're just going to fill in the blanks on the next two, but know that you can look back at this picture on page 499 in order to figure out how they're getting these values or how they're getting the fill in the blanks for here. So if I look back over here, the next one, if for integrals involving a squared plus u squared, let u equal, we're going to put a tangent of theta. And again, if you look back at that picture on 499, you'll notice that this a squared plus u squared, they're going to make that value the hypotenuse because it's adding the two legs together. Alright, so then if that happens, then we can set that up so that the square root of a squared plus u squared equals a secant theta. And last but not least, for integrals involving the square root of u squared minus a squared, so we have that first term being the term with the variable in it, we're actually going to let u equal a secant of theta. And for the square root of a squared minus u squared minus a squared, we have it being positive a tangent theta if u is greater than a, and we have it being negative a tangent theta if u is less than negative a. Or in other words, if that u happens to be negative. Alright, and then we have two special integration formulas down here below. I'm sorry, three. There's one on the next page as well. So the first special integration formula that we're going to talk about is the square root of a squared minus u squared. If we have the square root of that, it's just going to be 1/2. Make that a little neater. 1/2 times a squared sine inverse, or arc sine, whatever you like to write, of u divided by a, plus u times the square root of a squared minus u squared, plus c. The second one is 1/2 times u square root of u squared minus a squared times the natural log of the absolute value of u plus the square root of u squared plus a squared plus c. And this is when u is greater than a, that second one. And then for the next one on the third page, go ahead and pause the video so you can finish writing that down, and then move it on to the next one. On the second page, our third example, it's a little bit difficult to see, but it's u squared plus a squared. So the square root of u squared plus a squared, du would be 1/2 times u square root of u squared plus a squared ln of the absolute value of u plus the square root of u squared plus a squared plus c. Now again, these ones are special integration techniques or special integration formulas, so there are these special cases that you can use sometimes when they come up, but other times we're going to use these trig substitutions to not have a shortcut. Alright, now I noticed down here below it says section 2 down here is for application, so you guys can actually save that for tomorrow. But in your notebook, we're going to go ahead and do some examples. So this first piece was just the notes piece. Let's look at some examples. So pull out a blank page of paper or a blank page in your notebook so we can do these ones together. Alright, so we're going to be doing 3 examples. The first one comes from page 500 in your textbook. It's example 1 in your textbook, page 500. And it's for trig substitution. We're going to be using the u equals a sine of theta. So the integral that we're trying to evaluate is this integral here. The integral of dx over x squared times the square root of 9 minus x squared. And I want you to notice something. I want you to notice that in this integral they have a square root of 9 minus x squared, and that looks an awful lot like one of those properties that we just wrote down. So I want you guys to notice the similarities between 9 minus x squared and a squared minus u squared. So that makes u equal to x, that makes a equal to 3. So if we look at this in terms of the triangle, so I'm going to draw a little right triangle right here. Remember, this one is the 9 minus x squared. So I know that my 9 minus x squared is one of my legs. So I'm going to make it this leg here. And then because the 9 comes first, so a is 3, that means that has to be my hypotenuse, which means this one over here is just my x. So let's check my triangle to make sure that it actually works. So if I look at this in terms of the Pythagorean theorem, if I square this, I get 9 minus x squared. If I square this, I get x squared. If I add those together, I get 9, and I take the square root to get back to the hypotenuse, and that's 3. So that's good. This works in my Pythagorean theorem, which means that I did the setup correctly of this triangle. So I know that I have a couple trigonometric functions or trigonometric ratios that I can pull from this triangle. So I'm looking at x, all right? So if I'm looking at x here, and if I'm looking at this 3 here. Now the reason I chose 3 and not this 9 minus x squared is because I want it to be simpler, and I think adding in the 9 minus x squared piece will make it more difficult. So I'm looking at which trig ratio relates these two things together, and I notice that I have an opposite side and I have a hypotenuse. So opposite and hypotenuse is going to be sine. So I'm actually going to write that sine of theta equals x divided by 3, or in other words, x equals 3 times sine of theta. Now if you look back at your notes again, look back under the section titled Trigonometric Substitution. In the first example, it says let u equal a sine of theta, and so a is 3, so 3 sine of theta. That's exactly what we did. And I just want to show you that we can pull it from the triangle just as easily as we can pull it from our notes. And so the triangle, I think, will help you more on tests and quizzes and AP tests because it's more from a knowledge base rather than a memorization base. So we know x. Let's see what else we have up here in our equation. We need to know what dx, because we're asked to evaluate something that has dx in it. So if I can take the derivative of x here. So dx equals the derivative of 3 sine of theta is 3 cosine of theta. So I got that. We also need to know what 9 minus x squared, what the square root of 9 minus x squared is. 9 minus x squared. And I notice that I have it here in my triangle. So if I can find the relationship between these two, the ratio between these two, I can come up with something for that. So I notice that I have the adjacent side and the hypotenuse. So I have that cosine equals adjacent over hypotenuse. And if I multiply by that hypotenuse on both sides, I have the hypotenuse times cosine equals the adjacent side. So if I set that up over here, the adjacent side equals the hypotenuse, which is 3, times cosine of the angle, which is cosine of theta. All right. On this one here, dx, I forgot to add in that we have a d theta here, so make sure you have that there. Dx d theta equals that, so if I multiply the d theta over to that side, that's how I got that there. All right, and then last but not least, I have almost everything, all the pieces to substitute. I know what dx is because I have that here. I know what the square root of 9 minus x squared is. I have that here. The only thing I'm missing is this x squared piece, so I need to figure out what x squared is, and I can find that by just multiplying x times itself. So x squared equals, I'm pulling it from right here, x squared equals 9 sine squared theta. 9 sine squared theta. So now I have all the pieces I need, so I can substitute them in over here. So I'm going to take all these pieces and I'm going to substitute them back into the original equation, or the original expression. So I have the integral of dx, which is 3 cosine of theta, d theta, divided by x squared, which is 9 sine of theta, or sine squared of theta, times the square root of 9 minus x squared, which is 3 cosine of theta. So I'm looking for some things that cancel. I have a 3 here and a 3 here. I have a cosine here and a cosine here. So what I'm left with is the integral of, I'm going to pull out that 1/9 because that's a constant, the integral of 1 over sine squared theta d theta. And I can simplify that to 1/9 times cosecant squared theta d theta. And I'm running out of room a little bit, so I'm going to erase some of this stuff here. All right, now if you look at your table of basic integration rules, the integral of cosecant squared theta is negative cotangent theta. So if I write this up here, I have 1/9 times negative cotangent theta plus c. So if I simplify that, I get negative 1/9 cotangent theta plus c. And last but not least, we don't want to have cotangent in our answer because we didn't start with any trigonometric functions. We want to put it back into the form that we know. So if we look back over here at our triangle again, I'm looking for what cotangent of theta is so that I can substitute it back in. And I know that cotangent of theta is the reciprocal of tangent. So if tangent is sine over cosine, that means that cotangent must be cosine over sine. So if I'm looking for cosine over sine, tangent is opposite over adjacent, so cotangent would be adjacent over opposite. So that would be adjacent over opposite. So it would be the square root, I'm just going to write a little note over here, cotangent of theta equals the square root of 9 minus x squared over x. That's adjacent over opposite. So when I substitute that back in over here, I get negative 1/9 times the square root of 9 minus x squared over x plus c. And you can multiply that 9 into the bottom if you'd like to, but that's pretty much the final answer right there. So take a minute to go back through and make sure you understand what we did here. We're going to do 2 more examples together. This was one of the longer examples, so the next 2 will be fairly short. Alright, our next example comes from page 501 in your book. It's example number 2. So we're going to do another example for trig substitution. This time we're going to use a different format though. Recognize here that we have, again, another square root that has 2 perfect squares inside, and they're actually being added together this time. So that tells me that this piece is going to be the hypotenuse of my right triangle that I'm setting up. So if I have theta here, I know that my hypotenuse is going to be 4x squared plus 1. And if I think backwards to what my legs would have been, that means that one of my legs would have been 1, and the other leg would have been 2x. So if I squared those and added them together and then square rooted it, that would be the hypotenuse. So good, that all makes sense. So I know that u equals 2x. I know that a equals 1. So if I'm trying to set up all of my stuff again, I know that I have 2x equaling, if I look over here, I want to use this 2x. Remember we said we don't want to involve another x, that's going to get more confusing, so I'm going to involve the 1 instead. So I'm going to find the ratio of these two sides. That's an opposite side and an adjacent side. So I know that my ratio between opposite and adjacent deals with tangent. So this is my tangent one. So I know that 2x equals tangent of theta times that 1, but tangent theta times 1 is just tangent theta, so I'm just going to write that. So there's one trig ratio. If I want to find the derivative of x, dx, I can divide both sides by 2, so they get that x equals 1/2 tangent of theta. And the derivative of that would be dx equals 1/2. The derivative of tangent of theta is secant squared theta d theta. So I have one of the pieces of my puzzle now. I have dx. I know what dx is. I still need to know what the square root of 4x squared plus 1 is, so I'm going to work on that piece now. So the square root of 4x squared plus 1 equals, again, I don't want to involve this other x, so I'm just going to use this one and this one. That means I have an adjacent side and I have the hypotenuse. So that's cosine. However, if I do the cosine setup, let me show you really quickly what it would be like with cosine. If I said cosine of theta equals 1 over the square root of 4x squared plus 1, notice that if I do it this way, I have to multiply this piece over here, then I have to divide by the cosine piece over here. So what I'm going to do instead is I'm actually going to set up the reciprocal of cosine. So the reciprocal of cosine is secant. I'm going to set up a secant theta, which would be the square root of 4x squared plus 1 divided by 1. And now when I multiply the 1 over to this side, it's really easy to do it that way. So I'm going to use that instead. So I have that 4x squared plus 1, the square root of that, is equal to secant theta. So when I plug those two things into my integral, I get the integral of dx, so 1/2 secant squared theta d theta, divided by the square root of 4x squared plus 1, which is secant theta. One of my secant thetas on top cancels with the one that I have on the bottom. So what I'm left with, if I take out that 1/2, is 1/2 times the integral of secant theta d theta. So look back at your little handy-dandy integration chart, and the integral of secant of theta is, let me make some room over here. The integral of secant of theta is, well, take that 1/2 and keep it with us, the natural log of the absolute value of secant theta plus tangent theta plus c. And then looking back at our triangle that we drew up above, secant theta is hypotenuse over adjacent, so that would be the square root of 4x squared plus 1. Tangent theta is opposite over adjacent, so that would be 2x plus 1, or 2x over 1, I'm sorry, so we're just 2x. Absolute value plus c, and that's our answer. Notice that the answer to this one looks similar to one of those special integration formulas that we set up. The only difference is that our radical, the square root of 4x squared plus 1, was actually on the bottom. And because it was on the bottom, it kind of changed the form a little bit, but there is similarities that you can see back to those 3 special integration formulas that we wrote down, specifically to the third one that we wrote down. All right, we got one more example. All right, our last example is on trig substitution, but this time we have a rational power. So notice that we have, very similar to the last one, but this time we have a rational power of 3/2. So what I'm going to do with this is all of the examples we've been working with all have square roots in them. So we need to make that power of 2, the 3/2, that 2 from that, into a square root. So I'm going to rewrite this as dx over the square root of x squared plus 1, all of that to the third power. And that way we have this form, we have the x squared plus 1 underneath the square root. So if I set up my triangle, again I have the x squared being added to the 1, so I know that that's going to be my hypotenuse, x squared plus 1. I know that I have a 1 and I have an x. So if I check my Pythagorean theorem, that should work still. So that means that u equals x and a equals 1. So if I set up my little things that I know again, I know that x, if I have my right angle here and my theta here, I know that x, again, I don't want to involve this piece here because I think that's going to make it more complicated. So I'm only going to look at this one here and this one here. The ratio between the opposite side and the adjacent side is a tangent. So I know I'm looking at tangent. So x equals tangent theta, which is tangent theta equals x over 1. So again, if I multiply that 1 to the other side, it's not going to do anything. If I look at dx, the derivative of this, that would be secant squared theta d theta. Again, because I'm just multiplying that d theta over from the other side. And let's see what else I need. I have my dx. I need my square root of x squared plus 1. So the square root of x squared plus 1 is, again, the ratio between the hypotenuse and the adjacent side. And I want that square root of x squared plus 1 to be in the numerator. So that's hypotenuse over adjacent, which is the reciprocal of cosine. So it's secant. So that equals secant theta. Again, go back to your notes at the very beginning, the trigonometric substitution. This one is the second rule. So it even tells you there, those are like, that one's more for you to just notice that these are patterns that keep happening. We're always going to let u equal a times tangent theta, and we're always going to let the square root of a squared plus u squared equal a times secant theta. So I'm showing you from the triangles, but there's also these rules that are written down to show you the patterns that form. So from here, if we plug everything in, we have the integral of dx, so secant squared theta d theta, divided by the square root of x squared plus 1 cubed, so secant theta cubed, so secant theta cubed. So 2 from the top cancel with 2 from the bottom, and I'm left with 1 extra secant in the bottom. So that equals the integral of 1 over secant theta d theta. 1 over secant is the same thing as cosine theta, so I have the integral of cosine theta d theta. The integral of cosine of theta is sine theta plus c. And if I look back over here at sine of my triangle, sine is opposite over hypotenuse. So when I write my final answer, I get x divided by the square root of x squared plus 1 plus c. And that's my final answer. All right, that's it for today. We'll finish the rest of this section tomorrow. You can go ahead and work on your homework.